All right, AB students, this is another practice question for you for Thursday the 14th and preparation for our quest on Friday. So I think this is a nice question. It more or less pulls everything together from our unit 7, and so I encourage you to look at all the parts, A, B, and C. So grab a sheet of paper, go ahead and try this, and when you're ready, push play again, and we'll compare and check answers. All right, so part A says find the area of R, and fairly clear, I think, that region R is this red region here that I'm shading in. We're supposed to find the area of that. Okay, so it's the area between two curves, and we have some options here. We could use horizontal representative rectangles, like so. And these would work fine. The only issue here is I don't think this is the best way, because if we did do this way, we would have to split this region in half, right about where that blue dotted line is, because the lower part, the length of the rectangle would be determined by one curve, and for the upper region, the length of the represented rectangle will be determined by the other curve, which is actually a line. So we'd need two separate integrals. Nothing necessarily wrong with that, but I think there's going to be an easier way. So I'm going to go away from horizontal representative rectangles, and I'm going to go for vertical, and they would maybe look something like this. The reason why I think this is better is that for every single representative rectangle, the top is determined by the line and the bottom is determined by the curve. So there's going to be no need for us to use two separate integrals. So for A, I am going to write integral from I'm not sure to I'm not sure yet. I do know that it's going to be a dx integrand, because these representative rectangles are all dx wide or dx thick. But like I said, I don't know the limits of integration yet. I do know that I'm going to start on the far left there and go right, and the x value on the far left, certainly based on the description here, is 0. But then to find the end of the accumulation, it's going to be determined by this intersection point out there, and for that we'll need a calculator. And I've got an intersection point out there at x equals 1.4876644. And then if dx is the width, then the length of the represented rectangles, or maybe you could call it the height, would simply be the high function minus the low function. So I will write for that 4 minus 2x minus x cubed over 1 plus x squared. This is a calculator active question, so at this point I would use my calculator to figure out an approximation for the area of R. And when I do that, I'm coming up with 3.2145, so 3.215, I guess, if we round to 3 decimals. Okay, part B, find the volume of the solid generated when R is revolved around the x-axis. Okay, so if R is revolved around the x-axis, that has set up our representative rectangles automatically. They are going to be vertical, because remember that the relationship between the axis of rotation of those representative rectangles has to be perpendicular. And so they've got to be vertical representative rectangles, which automatically means they're going to be dx. But before we get too involved in that, we need to try to visualize the solid that's being formed. And I'm hoping that you will recognize that this air right here will get rotated around with the region, creating not necessarily a hole, because I think there won't be a hole, but there will be a gap in there, so this shape, this solid, could actually hold water if oriented correctly. And so because of that, we're going to be using the washer method. So as soon as I understand I'm going to be using the washer method, I'm going to write volume equals pi integral of big R squared minus little r squared, and I do know that they're dx rectangles, so go ahead and put dx right there. Okay, so limits of integration, I'm going to be accumulating from left to right, and so it'll be accumulation from 0 to that same x value, 1.48766644. And then the big radius, that would be the distance from the axis of rotation to the further away function. So that would be from this red dot to this other red dot. So the red line segment, that would be the big radius. That's simply the distance from the line to the x-axis. So that would be 4 minus 2x. So that's my first radius there. Second radius would be from the orange dot to the other orange dot, so that orange line segment. And so that, of course, is also a y distance, but it's equal to a different expression. For that one, the y is equal to x cubed over 1 plus x squared. It's the closer function, the one that's closer to the axis of rotation. Okay, so this is set up well with the washer method. The only thing we'd need to do now is to use Math 9 to approximate the answer. All right, when I did that, I got volume equals 31.8848, which would be 885, rounded to 3 decimals. Last but not least is C. C says the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. So notice how C is very different from B. B, there's a solid being generated by a revolution of region R. C, there's no revolution taking place at all. What we have here are cross-sections that are growing out or accumulating on top of the base, forming a solid, and we're going to be trying to find the volume of that solid. So I'll try to three-dimensionalize this a little bit. There is one of the square cross-sections, something like that. There's another one, of course, that'd be a little bit smaller. There's the smallest one yet. A little tiny one on the end. Hopefully that makes sense as far as what those cross-sections might look like in perspective. So, once we've recognized that we're finding volume by cross-sections, there is no pi involved on this one. I'm going to write volume equals the integral. We don't know yet. We just need to recognize that these cross-sections are going to be dx wide. So my integrand is going to be in terms of dx. My accumulation pattern is going to be just like the other ones. We're going to accumulate from left to right. So I'll start accumulating at 0, and I will stop at that 1.48766644 number. Okay, and then lastly, I need to plug in the area formula for the cross-section. The cross-sections are all squares, so this would be side squared. And then finally, we just need to plug in the length of the side of one of the squares. We'd go from this red dot to that red dot, of course, or from this one to this one. These are all side lengths of the square, and you can see that they are going to be all different lengths depending on where you are in the region. So it's going to have to be a variable expression, and hopefully you saw that all of those lengths are simply going to be depending on the height of the line minus the height of the curve. And so in here for my side length, I'll put 4 minus 2x, which is the line, minus x cubed over 1 plus x squared, which of course is the curve. That'll give me the side length of the square. Squaring that'll give me the cross-sectional area. Once again, it'd be time to turn to Math 9 to figure out an approximate value for this volume. And when I do that, I get volume is equal to 8.997, rounded to 3 decimals. All right, so I hope that went well for you. As I mentioned earlier, this covers basically the bulk of what we did in Unit 7. Feel free to mess around with this a little bit more. I would say one place you could do that would probably be Part B. If you wanted to change the axis of rotation as something other than the x-axis, might be a good opportunity to come up with something a little more interesting. But other than that, I think this covers just about all of it. So hope you're having a good day, and keep studying, keep preparing and practicing, and be ready for your quest tomorrow.